Hi, and welcome to Code Corner from Mayfield Renewables. My name is Ryan Mayfield, and today I'm going to talk a little bit about module level power electronics, or MLPEs, as it relates to the 2020 National Electrical Code. MLPEs have become quite common in our PV systems, and there are a few code sections that are specific to how we apply these, specifically around voltage and current values. And so I'm going to take a few minutes just talk about those, point out those specific code sections and how they apply to our systems. So before we jump into the MLPE specifically, or looking at the systems, I guess, it's helpful to look at the definitions. So in the 2020 code, we have a definition, or we have definitions for both of the types of MLPEs we're going to talk about. The first being DC to DC converters. So you see the language here from straight from the code, device that can provide an output DC voltage and current at a higher or lower value than the input DC voltage and current. So basically, this DC to DC converter is a pretty broad definition. It can just be something that is going to take DC in, DC out. That converter may or may not, do something with that voltage. It may do a boost on the voltage. It may buck the voltage. It really depends on what the system is, the exact configuration for that MLPE. It could be just a specific system to help you meet your rapid shutdown requirements. So there's no one specific thing that it does. It can take a few different forms. In code, we have it being very generic in terms of this definition, and that's done pretty purposefully because then we can apply the same requirements. Doesn't really matter if it's an optimizer or if it's a rapid shutdown device. The requirements are really going to be just about the same in terms of voltage and current values. The other one is a definition for inverter, equipment that changes DC to AC, pretty straightforward stuff. So the other parts, or the other MLPEs that we're going to see out there in our systems, are microinverters. So we have microinverters that are directly connected to modules. That's just another way of using module level power electronics. That MLPE term I should have said earlier is it's kind of broad based. It's just power electronics that are connected to individual modules, or modules, maybe two modules. And so we're putting these electronics at the module level for whatever reason, very often for rapid shutdown, sometimes for optimization, but we really have either DC MLPEs or AC MLPEs, which are microinverters. So let's take a quick look at just some images here on kind of what these look like in terms of in our system. So starting with the DC to DC converters, pretty generic. And so what we're doing is here we have modules connected to individual DC to DC converters. Those can be varying in string length. So we can have a bunch of them put in series. We could have very few put in series. It really depends on your system. But really the overall system, what we're looking at here is, we're going to have these individual modules going to individual MLPEs and connected to some sort of a power electronics like an inverter, where it's going to convert the AC to DC and connect to our utility system. So this is a really basic, straightforward utility interactive system that you can see here. Pretty common use of DC to DC converters in the PV industry. The other just kind of picture to show is our microinverter system. And so in this case, we're taking DC input from those same modules. Instead of converting it, just doing some sort of a DC to DC conversion, we're doing DC to AC conversion right there. And then, we don't have that. Those are our inverters. We don't have to have an additional inverter, and we're interconnecting with the utility. Definitely some pros and some cons on both of these systems. And this is a very common way of doing residential systems. We're seeing lots and lots of microinverter systems. And so this is just a way of meeting multiple code sections with the equipment, with using the MLPE equipment that we have accessible to us. Okay, so now that we have those kind of pictures, broad system types that are defined for us, a few of the code sections that I wanted to talk to you about. Again, there's some very specific, some that are very specific for our different MLPEs. This one, 690.7 B2, this is specifically talking about the voltage output for our DC to DC converters. I skipped B1, which talks about a single DC to DC converter in series. You can go and look at that if you need. B2 is where we're going to see most of our systems. We're going to have multiple DC to DC converters in series. And so what we need to do is, in order to figure out what the maximum system voltage is, this is going to be a little different than our old systems where we would just take PV modules and string them together. In this case, we are looking at the spec sheets for the DC to DC converters. And sometimes we also have to look at, as we're looking at in this image, the connected inverter. And so to understand what the maximum system voltage is we need to look at the system as a whole. How are they working together? So DC to DC converters, the language tells us that the maximum system voltage can be determined in accordance with the instructions included with the DC to DC converter. So in the case of what we're looking at here is we have a very specific type of system, a solar edge system, where we have a specific DC to DC converter. It has to match up with a specific inverter. That's a system that they work together. And so this, by looking at this, this is telling us that the maximum system voltage for this specific system for these specific inverters is 1,000 volts. Now, if you're using a DC to DC converter that is only going to be doing rapid shutdown functions, for example, the voltage just passes through. And so you have to look at the instructions, the manual, and understand how that system acts, how those voltages react. And so you're going to have to use that to determine what your maximum system voltage is. If for some reason the manufacturer doesn't give you this information, the maximum system voltage is going to just be the maximum output voltage listed for those DC to DC converters, and you're just going to add up the series connections. So I've yet to find anyone who doesn't have this listed in their instructions. So that's really going to be the way that you're going to go about finding what the maximum system voltage is for systems utilizing DC to DC converters. Now moving over to the current side, and so the MLPEs, sticking with DC to DC converters, the output circuit current value is something that we have to be concerned about when we're sizing our circuits, figuring out overcurrent protection, size of our conductors. And so this section, 690.8 A1D, talks about the output circuit current for our DC to DC converters. And it references back to A1C, which is just one previous code section above this. But in essence, what we're looking at here is the output circuit current, the maximum output circuit current, is going to be whatever the DC to DC converter says that it is. So what this means is that we have PV modules connected to our DC to DC converters. Those converters are listed by UL 1741, and that output voltage, the output current that is coming out of the DC to DC converters, there's a limit to it. It can only put out so much. And so that will be part of the listing process. So your DC to DC converter manufacturer is going to say output current is 15 amps, 18 amps, whatever that value is. That number is that maximum value. Doesn't really matter if what is coming in on the input side. You could have a higher current coming in on the input side. The output is going to be regulated by the converter. It's a piece of power of electronics. And so it's going to regulate and limit the amount of current that it can come out. And so that's the value that you use. On the flip side of all that, if you have a PV module, kind of extreme example, let's say you have a 5 amp input and the DC to DC converter says it has a 15 amp output, sizing your conductors per code, what you're going to do is you're going to size it based on that 15 amp value. And so this is just a way that we're going to size our conductors, our overcurrent devices, using this code section when it comes to our DC to DC converters. And then the other one is the output of our microinverters. Those are inverter output circuits. So this is really nothing new. This is, you're going to size this circuit exactly how you would a string inverter or anything like that. And just like the DC to DC converters, the output current is regulated by the listing. And so if it says that it has a 15 amp maximum output, that's all it can do. It doesn't matter what the input value is. And so again, you're going to use that value as your basis of design for figuring out your current and your overcurrent protection and your conductor sizing as it goes for inverters. So that covers our module level power electronics and a couple of the very key code sections as applies to voltage and current on those. Thanks for tuning in, really appreciate it. And if you have any specific questions around any of the codes things that we've covered, or if there's topics that you would like to see covered in future issues, please let me know. Feel free to reach out. Thanks a lot.